the stack for fun and profit. So it's the first time that the rest of us become aware of how to actually write and exploit software to do malicious logic. And then we go forward from there. In 1997, we get to the Return to libc. That's the seminal paper on how to get past stack execution prevention. However, since most of us don't have stack execution prevention, it goes largely ignored. And it becomes largely ignored up until it becomes a problem much later in the 2000s. But beyond then, 2003, we get IDS becomes commonplace. Most of us have it. Comes default on our software. We use Zone Alarm, we use Checkpoint, we use something, and it becomes widely known. 2003 is when we get the first kind of commercial exploit framework via Metasploit. I think the best description I heard of Metasploit right when it came out was, this is like the ice cream man handing out dynamite to kids. I think that's fairly accurate. Then the other thing that came out of Metasploit wasn't just that it was an exploitation framework, but it was the first introduction for most people to memory-resident-only malware. And the reason that's important is all of the forensic techniques that we've been using to control malware are now invalid, because this thing leaves no forensic artifacts whatsoever on the drive. And so if it bypasses your IDS and your IPS, now you're in real trouble. So not surprisingly, right around 2003, researchers start taking a look at, well, how do we even examine malware? And you get the Princeton frozen memory example. Neat parlor trick. It was great at the time, but not very useful. Not many of us want to.
Hi folks, I'm Gig here. Unfortunately, we had some technical difficulties, and we don't have a speaker or audio until about the 2-minute, 3-second mark. Sorry for the inconvenience.
Perpetrated malware that actually gets around two-factor authentication. It does so by actually borrowing the credentials that are on smart cards. So we're not even safe via 2FA. In 2011, we get the first instance of quote-unquote next-generation firewalls. Notice that that doesn't actually address any of the previous things that haven't been mitigated yet. So we still have problems with return to libc exploits. We still have problems with return-oriented programming. And we still have problems with two-factor authentication being taken advantage of by malware. So, why are we here? Well, most of us that are in this field are not computer scientists. Some of us are. Are there any computer scientists here? I'm just curious. Yeah, so 2, 3 if I count myself. We still have to find a way to mitigate these threats on the networks. We have to understand. Now, computer scientists have a little bit of a leg up, because when we go through our degree programs, we learn about computational theory. And it's a class we all suffer through called Automata. I don't know anybody that thinks that Automata is fun. Did either of my computer scientists think that Automata was fun? Okay, there's normally like one sick individual, so it's good to know who that is. It's not fun, but it's critically important. And it's critically important because computational theory allows you to detect snake oil. Right? And so recognizing snake oil helps you avoid having some discussions that many of us have either had or heard, and it goes something like this. Somebody comes in from the organization and goes, the cost of the breach is just too damn high. We got to do something about this. Please make it go away. Right? And so some vendor shows up with a shiny black box with a bunch of blinky blue lights, and it's very pretty. And they throw the sales speak at you, and they tell you that their next generation, I think we're like on our 4th or 5th generation now, their next generation box is full of ODay detection, and they're just going to absolutely save you. We start to tear up a little bit. We go, that's fantastic. You're going to save us from all the evil hacksaws. And the vendor goes, yeah, absolutely. Yeah, you can trust us. Just give us your money. We'll save you. And we start to believe the hype. And then they throw a bunch more sales speak with a bunch of industry terms that all amounts to magical pew-pew. And they promise that they're going to keep us safe. And we just throw gobs of money at this. Gobs and gobs of money. And about like 3 to 6 months later, the APT comes along, and our network's on fire. And APT is basically anybody that got past your next generation magic box of pew-pew. Or in this case, a 12-year-old with a dial-up modem and a copy of Burp Suite. So part of the problem is if you go to these vendor sites and and you read the pages, you see all of this like magical terminology, and you'll read the page, and you'll get really excited about it, and you'll want to go buy whatever that product is. And if you stop and you think about it, you realize that you have no idea what this product does, or how it works, or how it's going to help you at all. And they've got these magic terms like state-of-the-art and adaptive defense and virtualized cloud-related digital DNA, big data, software-enabled, end-to-end multi-layer hunt threat analytics platform. What does any of that mean? No, that's a serious question. Does anybody know what any of that means? Here's my favorite one. I gave a shorter version of this talk at B-Side San Francisco, and then I left and I went to go to SANS 2016. I walked to the sales floor and I saw this. Cloud over IP. First of all, the salespeople didn't think this went through because COIP sounds like something you cannot say in polite company. Right? Second of all, I had two thoughts. The first one is, hey, genius, cloud is made of servers. And then I kind of looked at the vendor like this and went, what are you selling me? What are you promising? So how are we going to get past this marketing speak? You know, how am I going to go to a vendor, and when they talk to me and they try to sell me the sales speak, how am I going to get past it? Well, that's easy. We're just going to computer science the hell out of it. So Automata, there's this guy, you know, good-looking guy here. His name's Alan Turing. You may have heard of him. He was recently in a very bad movie. He is the father of modern computation. And because of that, when we develop these mathematical models that describe every computer you've ever used, they're called Turing machines. Okay? And it's just an abstract machine used to prove the fundamental limitations of computers. And something is said to be Turing complete if it can theoretically represent everything that you would do on a computer. Right? So it's a language or a machine that can accomplish all the tasks that you would accomplish with a computer. And so we have to suffer through this class called Automata as computer scientist. And what it is, it's really just a math class. It's a math and logic class that studies what problems can and cannot be solved by computers and which problems can be solved easily and harder. So all of you are going to get the salient points of Automata in about 35 minutes without having to suffer through an entire semester of it. So generally speaking, and we use slightly different terms, but computer science problems can be put into three categories. They're solvable, intractable, or undecidable. If they're solvable, they're easy. They can be solved in something called p-time or polynomial time. And what that means is that the amount of time that you solve it is some factor of the amount of input that you give it. Harder problems are called intractable, and what that means is that the running time of that problem is an exponential of the input you give it, and some of them are undecidable, and you're just never going to solve them with a computer ever. It's not a matter of processing power. It's not a matter of time. It's not a matter of, just having. We're going to get to an example of a problem that cannot be solved. I'm going to show you that. So what we're going to do is we're actually going to go over an intractable problem, and we're going to go over an undecidable problem, and I'm going to show you why you care. That's the whole reason of this speech. So let's talk about a hard problem first before we get to the impossible. So this is a very famous problem. It's called the traveling salesman problem. And it's a fairly simple problem, deceptively so. So given a list of cities, what is the shortest possible path that takes you to each city only once and returns the originating city? And you have to find the most optimal path. That's the trick. It's not just, hey, give me a path. I want to find the most optimal way to do that. So in order for it to be the most optimal path, there is only one. And the only way for me to find out what that one most optimal path is to try every path. Okay? And it turns out that this is really hard for computers. Who thinks that this is really hard for humans to solve? It doesn't sound hard, right? So why is it hard? The correct answer. That's kind of the kicker. So let's start out simple, right? Let's say we just have 5 cities that we want to visit. 5 cities seems pretty simple. And let's assume that we'll make this easy. You can get from any city to any city. For you network geeks out there, this is a full mesh. Okay? So we're going to start at any one of the 5 cities. We'll just pick one. So we start out at one of the cities, and then we have 4 choices to choose from. And once we get to that second city, we now have 3 choices to choose from. Yeah, that's right. You know the song. Sing along. And then we have 2 cities, and then we have 1 city. So how many combinations do we have? Yeah, 5 factorial. So that's 5, 4, 3, 2, and 1. 5 factorial. So for just 5 cities, I have to try 120 computations. 120 computations doesn't sound very large, but who has a problem set of only 5? So this traveling salesman problem runs in n factorial time, as was pointed out. And so if you want to find the most optimal path, because you're going to do a cross-country cannonball run, and you're going to go from New York to San Francisco, there are 19,354 registered cities. And you have to try every combination, because you have to find the one optimal path. So 19,354 times 19,353, so forth and so on, until you get to 1. And if you did one calculation per millisecond, it's going to take you 110,000 centuries to find the correct answer. Doesn't seem so simple now, right? Seems a little bit harder. So you go, okay, that's great, but who cares? It's kind of a toy problem. I mean, how is this really useful? Well, it turns out that traveling salesman is analogous to a lot of problems that we want to solve in InfoSec, right, or networking. So routing is a traveling salesman problem. Detection of man-in-the-middle attacks or race conditions is a traveling salesman problem. Resource use optimization is a traveling salesman problem. Search algorithms, crypto problems, basically anything where optimization is required, it's a traveling salesman problem. And if the traveling salesman problem is hard, and all of these problems are analogous to it, that means that all of those problems are also hard to solve via computation. Now, right at this point, somebody, usually a young kid in the back, goes, dude, I got GPS on my phone. Traveling salesman is easy. Okay, so GPS does solve a problem, right? It will get you there. Is it the most optimal path? Well, GPS works because it makes a lot of assumptions, right? And sometimes the assumptions make sense. It's going to make assumptions like, hey, look, interstates are going to be faster than farm roads. And so it's going to toss out all of the farm roads. And then it's going to look and it's going to go, hey, rural routes are much faster than farm roads. And it's going to toss out the farm roads. And then you're going to tell it things like, hey, don't show me any toll roads. And so now you're going to drastically reduce the number of combinations. And on top of that, the GPS can do things like, hey, anything that's a loop I don't want to do. And I always want to be making positive progress. I don't want to loop back on anything. And those assumptions drastically reduce the problem space. Okay? And if the assumptions are good, you're going to have a workable but non-optimal solution. The problem in security is non-optimal means you're going to have type 1 and type 2 errors. You're going to have false positives and false negatives. And in information security, we want to be right all the time. We're just not going to be able to get there via the solution. So, what does GPS look like non-optimal? Right? Who's ever had the GPS tell them to, turn left into a building or turn right and the exit's not there? So that's what happens with non-optimal. But because there's a human in a loop and it's not an autonomous vehicle, we can go, yeah, GPS, I'm not listening to you, and I'll listen to your exasperated recalculating again. So traveling salesman problem is hard. It's not impossible, but it's hard. And you can solve it. You can arrive at a solution if you're willing to make assumptions and you're willing not to take the one correct answer. If you're willing to accept it within a range. So if the vendor tells you that they're solving a hard problem, go through and ask them why. Hey, what assumptions are you making? Are you getting rid of toll roads? Are you getting rid of farm roads? How did you do that? So now let's talk about the question that was asked earlier. Show me an impossible problem. The halting problem. The halting problem is an impossible problem. The halting problem is something that is very difficult for most people to understand, so we're going to take a shot at it. So let M be an arbitrary Turing machine with an input alphabet of sigma, and let omega be an element of all the possible combinations of sigma star. Will M halt on an input string omega? What does that mean? No, nobody? Okay. All right, let's try it. Let's try picture. So there it is. There's your computation machine. There's your input, your machine M, and your sigma, and it's going to go through and compute, and it's going to solve whether it stops or not. Not better. All right, so everybody's familiar with the KISS principle, right? Keep it simple, stupid. All right, let's try it. So, KISS principle. Given a computer program and input, you cannot determine if a program will ever finish running via automated means alone. right? So I give you a program and I give you an input string. Can you tell me if that program will ever halt? Will ever stop? Not give me the correct answer. Can you ever just even tell me if it'll stop? And it turns out that you can't do that. Well, why is that? Seems pretty simple. So let's consider the options, right? You give it an input and it finishes. Woohoo! It stopped. That's great. Now we know. What if it doesn't stop? What happens then? Why did it stop? Well, maybe it's stuck in an infinite loop. Or maybe it crashed horribly and it's not going to exit normally, ever. Or maybe you just haven't clicked that pop over for the Windows 10 upgrade. I don't know. But the point is, if it doesn't stop, you don't know why it hasn't stopped. Maybe it needs more processing time. Maybe it just hasn't finished calculating. Maybe it's crashed. Maybe it's an infinite. And you just don't know. And there's no way you can know that. And because of that, this is not a problem that's solvable via automation. Because if you let it run and run and run, you never get the output. At some point, you go, well, I don't know. Let me just hit Control-C. Well, what if it just needed to process like 1 more second, or 2 more seconds, or 3 more seconds? You just don't know. You can't know. So why is this useful? Well, certain problems, like the halting problem and the traveling salesman, are either provably undecidable and can never be solved by automation, or they're hard. And you should recognize those. So when a vendor comes to you and says, hey, look, I've solved this hard or impossible problem, here's how you tell them that they're full of it. You assume that they have solved it. You're like, you know what, Joe, Julie, I believe you. I believe that you've solved that problem, and you can detect all O days with your shiny new box of Pew Pew. And then I'm going to take your algorithm, and I'm going to package up that algorithm and put it into a magic chip, and then I'm going to see if I can use it to solve an impossible problem. And if I can use your solution to solve an impossible problem that cannot be solved, you didn't solve your problem either. It's a proof by contradiction. So the vendor says, we detect O days, and they're sneaky. They're sneaky people. It's not because they're bad people. They just have a job to do, and they got to feed their families too, right? But they say, we detect O days. And we hear what we want to hear. We hear, you detect all O days, right? So let's assume that's true, right? We're gonna take their little magic chip, their magic inside chip, and we're gonna put it in an ASIC. And then we're gonna build the halting problem solution. And we're gonna take that little magic chip that detects all O days, and here's what I'm going to do. I'm going to say that anything that is an O day will halt, and anything that is not an O day will not halt. And I've just solved the halting problem. Except that I can't solve the halting problem. And since I can't solve the halting problem, you can't solve the O day detection problem. Does everybody understand how that works? So when they tell you that they've solved one of these problems, they can't. They can't do it. Except that MIT did do it. Right? April of this year, April 16, MIT builds artificial intelligence system that can detect 85% of cyber attacks. Anybody see this on like Hacker News? I got like 400 emails when this thing came out. It was awesome. And I went, that's interesting. Let me read this. What assumptions did they make? Because I really don't believe we got the mission accomplished. Mostly because I need a job still, and I can't have them solving this problem. So I went to the MIT site, and I took a look at their documentation. Here are the assumptions. Presents its findings to a human analyst. And then the human analyst identifies which events are actual cyber events and which ones aren't. So you didn't do this via automation. You built a really fancy firewall. Right? Okay, all right. But that's okay. I'll take a fancy firewall. But let's look at that 85%. 85% is pretty good, right? 85% is a B average. I like B's. I like A's better, but B's are all right. So let's take a look what that 85% is. Let's do some math here, because I like the maths. Let's say that 1/100th of a percent of people can write one zero-day exploit a year. 1/100%. I think that's reasonable. 1/100th of the population should be able to write 1 O-day a year. China has 1.357 billion people with a B. So 1/100th of a percent is right around 13,500. So that's 13,500 new O-days a year. 85% of that is 11,000, 11.5 thousand, which leaves me just over 2,000 unidentified zero-day attacks per year that are never going to get detected. And oh, by the way, there's some other assumptions there. We're assuming that we're actually going to be able to block instantaneously 100% of the attacks. And oh, by the way, since the machine is sending it to human operators, those human operators are going to make that decision instantaneously, and they're always going to be right. So 85%, not so good. Really not so good. So what about malicious traffic and TCP/IP? Well, it turns out that TCP/IP is Turing complete. Turing complete means halting problem applies. Halting problem applies means that I can't tell you if any given packet is malicious or non-malicious. So that next-gen firewall, probably going to make things a little bit better, but it's not going to solve all your issues. It is not going to detect all bad traffic. And it's just going to include different signatures, either heuristic or signature-based, but it's just statistical models and signatures. It is not fundamentally new. And it is not going to solve your problem. And then there's one more bit. There's the von Neumann architecture. Von Neumann architecture is the architecture of every computer you've probably ever touched. There are some high assurance systems that use a slightly different architecture, but right now it doesn't matter if you've got a smartphone, a desktop, a laptop, a mainframe. They all pretty much use the von Neumann architecture. What the von Neumann architecture does is the memory space for instructions is the same memory space as it is for data. And because they're encoded in the same ways, you can't tell the difference between data and instructions. And absolutely every exploit that has remote code execution takes advantage of this. Why? Every exploit that you've ever seen asks for input from the user. They get unexpected input, and then that input is treated as an instruction by the central processing unit. So that hex 41 at any given instance may be a capital A, or it may increment the ECX register, and you just don't know which. And you can't know which, and the computer won't know which, and that's how all of these exploits work. So it's pitch black. I've given you all bad news. You're likely to be eaten by GRU. We can't optimize resources. We can't identify malicious logic. Can't tell you if you're reading an instruction or data. And I can't even tell you if a program will stop. Who wants to quit? Bar's upstairs. Let's go have a drink. All right, let's not do that, right? So, Grace Hopper, pretty smart lady, she invented compilers. She said, presenting a problem without a solution is called whining. I don't want to whine. I want to give you some solutions. So how do we live with no ODay detection? So we kind of covered this already. Some vendors are going to claim that they do ODay detection, and they might. They're going to detect some ODays. Absolutely. They're not going to detect all ODays. And the way that they detect some ODays is they're going to use some heuristics and some signatures, but sooner or later somebody's going to either break that statistical model or they're going to tweak their binary so it bypasses the signatures, and they're going to get through. And what they're really doing is they're making some assumptions to reduce the problem space because they can't solve the problem otherwise. So what we really need to do is we need to go through and we need to validate those assumptions. So what does that look like? I'll give you an example. I recently actually personally had this happen. A vendor came into my office with a bunch of PhDs. I am not a PhD. But they came in with a bunch of PhDs with 100-pound heads, and they claimed that they had a, quote, next-generation vector algorithm for behavior-based network modeling that can detect all malicious traffic on a network. What in the wild world of sports is a next-generation vector algorithm for behavior-based network modeling? Right? That's when my little, flag goes up, and I go, well, that sounds like snake oil. Right? So, does this sound like a valid claim? I don't think it sounds very valid. Does that mean it is completely useless? Well, no, I didn't throw them out. I said, all right, sit down. Let's talk about what you have. So how could this be useful? Let's assume that I have an industrial control system or a supervisory control and data acquisition system, right? ICS SCADA. Why am I picking that one? Why? Because it's horribly broken, right? I don't know anybody that has anything nice to say about ICS SCADA. And I don't like using problems. So let's choose a hard problem, right? So ICS SCADA, they use their own protocols, right? They use things like Modbus, and they're limited protocols, and we understand those protocols, but those protocols are also Turing complete, which means the halting problem applies, which means that I cannot detect all malicious traffic using that protocol. And I know that. So let's talk about what some helpful assumptions might be. Well, the first one is that ICS SCADA networks shouldn't be talking to non-ICS SCADA systems, right? If I see Facebook coming across my ICS SCADA network, there's a problem. Only certain components should be able to talk to certain other components, right? The way these things are laid out, they're meant to do very particular processes. And so not every component should be able to talk to every other component. And so if I get a message at a component from somebody it shouldn't be talking to, that's anomalous, and I should at least investigate it, if not deem it outright malicious. Then on top of that, ICS SCADA systems are cyber-physical systems. So there's the cyber side, but then that SCADA controller is going to control some remotely operated valve or some pump or some centrifuge, and that thing has some physical limitations. It can't operate above a certain pressure. It can't operate above a certain temperature. It shouldn't be operating at various speeds. It shouldn't be operating on the weekends. It's got some sort of physical limitations. And then on top of that, there are some ways that I employ this thing, right? If I've got a car, I can mash down the accelerator, but that's not the way I normally operate it, right? And if I have a teenager and I let them borrow my car and they're going from 0 to 60 in 4.9 seconds, I probably want to know about it because that is anomalous activity, right? So you take it and you draw your little Venn diagram and you go, okay, well, here's the circle of all the valid message protocols. Right? And then on top of that, I'm going to overlay that with all the physical constraints of all the pumps and all the valves and all the pipes that are controlled by this. And then I'm going to overlay on top of that, here's how I would normally expect this to be. So instead of looking at any one of these circles, which is very large, I just have to look at that overlap. And I go, listen, anything outside of that overlap that's either not a standard protocol or outside of my physical constraints or outside of the way that I normally operate this network, I should probably be aware of that. I need to be notified. Now, some of it, I'm going to take a look at it as a net admin, and I'm going to go, some of it I just need to be warned about so I can go by and look at it. Some of it I'm going to go, you know what, just shut it down. Make it stop. But that's a decision that I'm going to make as a human. That is not a decision that the computer makes on its own. Now, can I put that into the computer and go, listen, if you see this, shut it down, or if you see this, just give me a pop-up and let me go look at it? Absolutely. But the human still has to make that determination. So what about now somebody goes, but Stuxnet? Yeah, I got it. Stuxnet, right? So what happened with Stuxnet? Stuxnet altered the output of the SCADA system, so what you didn't get back from the controller was the correct speed, or the correct temperature, or the correct pressure. Here's a radical thought. Go look at your stuff, right? Cyber physical systems. Get up off your butt, leave your console, and go look at your stuff. I guarantee you that there is an analog pressure gauge there somewhere. There is an RPM meter. Listen, folks, I drive a 40-year-old car with no electronics for a reason. Okay? Go look at your stuff, right? Physical sensors are not convenient, but they work and they're not hackable over the internet, right? I mean, ideally your ICS SCADA isn't on the internet, but they're not hackable via electronic means. Now you're down to a physical security problem. We know how to solve that. And then trust but verify. Don't always just believe your automated sensors. Yeah, they're convenient, but they're not a substitute for putting your eyeball on your stuff. So automation is not going to solve all your problems. You still need smart people. So invest in your people, train them properly, and reward them for doing good things. So key lessons, almost no problem of interest can be solved optimally by computation. It just can't be solved optimally by computation alone. You still need smart people. We can solve portions of these problems by making assumptions and understanding the risks we're accepting. And those need to be conscious choices. If you're the decision maker, you need to understand the risk you're accepting. And if you're not the decision maker, you need to explain to the decision maker the risk they're accepting. It is really, really easy to get angry in this field. We all get emotionally invested because we spend way too many hours at work. But at some point, you got to realize it's probably not your risk to accept, and you need to explain it to the boss. Okay. Different vendors are going to make different assumptions. And so while it's really convenient for us to manage networks where we've got all the same color box, because they all make the same assumptions, it's probably not the safest way to do that. You're probably much better off going with a combination of vendors that are going to have different assumptions so that if the first box doesn't catch it, maybe the second box does. And understanding the fundamental limits of computation are going to help you identify snake oil. Again, vendors aren't bad people, but they got a job to do. And automation is going to help you reduce the noise, but at the end of the day, you as a human have to look at this thing. Firewalls are great, but if you're not reading the logs, shame on you. So for the vendors, I love you guys, but please be honest in your claims. Your users, your customers, we're not stupid. right? And if you lie to us, we're not going to give you our money. Send me an engineer. God bless salespeople, but they can't answer my questions, and I ask hard questions. I was actually very happy. I walked up and down and talked to some of these vendors, and most of them actually sent engineers, which I thought was great, because I could ask real questions. Assumptions and methodologies for the vendors, they're non-secret sauce. They're not. And if you think they're secret sauce, then fine, have me sign an NDA, but explain to me how your product works so I can make an informed choice. If I'm spending $250,000 on a sensor, I want to know how it works and if it's going to solve my problem. And quit, for the love of God, selling us marketing speak. Next generation, cloud-enabled, software-defined, heuristic-based, virtualized, threat-centric, multi-layer, end-to-end, adaptive analytics, cyber defense, pew-pew isn't worth the shiny paper it's printed on. Tell me what your product does and how it does it. So for the customers, the vendors do have some smart tools out there. They are worthwhile tools. We spend a lot of money on it because they're smart tools. But if the claim is too good to be true, it probably is. It probably is. And they need to explain to you how they're solving these problems. If you're spending the amount of money that we're spending on InfoSec products, you should understand how the product works. Ask them how they're reducing the problem space. Ask them what assumptions they made to get their product to solve these harder impossible problems. And then make sure that those assumptions are valid in your operating environment. Right? If you were going to buy that vector-based heuristic modeling network and you weren't using an ICS SCADA system, you would have to use very different assumptions because my assumptions are not valid in your operating space. And then really, human operators and hunting combined with defense in depth, they're always going to be your best solution. It's always a combination of these factors. So really, the next time a vendor tries to sell you Brondo, the Ode mutilator, make sure you ask them how they solved the halting problem. So next time you're walking around a vendor watch, there's your vendor bingo card. Lots of people cried bingo at SANS 2016. Are there any questions? Okay, ladies and gentlemen, thank you very much.